Okay, welcome back, everybody. We're going to finish this lecture off now, and that will be it for this lecture, this virtual lecture we're going to have on Wednesday here, which is today. So, what are acids? We talked about acids a little bit in the last module, and I told you basically acids, especially strong acids, are the ones that will dissociate completely in water, and weak acids are ones that will only partially dissociate, right? And we were able to discuss like which acids were strong and which acids are weak and stuff like that. Well, we're going to dive a little bit deeper about acids now. So ionize means like disassociate, right? And so acids are basically substances that when you put them in water, that's another word for aqueous, right? They form positive H pluses. They form H plus ions, right? We also call these things protons too, right? We call these things protons. That's basically what they are, right? So you'll hear me go through this lecture and use those two words interchangeably, a hydrogen ion or a proton, right? And in Gen Chem 2, you'll get even deeper and they'll call it other things too. But just know that here I'll use H plus and protons interchangeably. And so because H plus consists of only a proton, acids are often called proton donors, right? So when an acid is introduced into water, it will donate protons, right? So here's some examples of some acids, right? We have hydrochloric acid, really strong acid that's in your stomach. Nitric acid, also very strong acid. Sulfuric acid, another very strong acid. And then a weak acid here, which is acetic acid, the same thing as vinegar. And I just want to make clear to you that this color scheme that we have right here for different atoms, it's pretty much universal convention in chemistry, right? You see a white one right there, it's always going to be a hydrogen atom. A red one will always be oxygen. Blue one will always be nitrogen. Carbon is always going to be black. Sulfur will always be yellow. And then chlorine will always be green. And so when you look at these space filling atoms of each of these molecules here, just know what those atoms mean. And if I were you, I would just memorize that stuff because you'll need it later for chemistry, for organic chemistry. So what are bases then? If acids donate protons to water, bases accept protons, right? They will accept protons. Remember, I use this interchangeably, protons, right? And usually when they go into water, they actually increase the hydroxide concentration, right? And we talked about hydroxide before. Hydroxide is the polyatomic ion that has a hydrogen and an oxygen and a negative charge. That's hydroxide right there. So generally, what I'll say to people when we first start learning about acids and bases is this general phrase here, where acids donate protons in solution, whereas bases donate hydroxides. Into solutions. That's the simplest law of acid-base theory right there, right? We'll talk more about laws of acid-base theory later, but those are the simplest right there. And so these hydroxides right here, of course, are negatively charged, right? Notice right there. So they can easily accept protons, right? They can easily accept protons and grab a proton, okay? And when they grab a proton, you basically make water, but we'll talk about that later. And so here we have water right here, and then we have a base right there, which is ammonia. And you can see here how this base here will remove one of the protons right here, right? So before we had two H's, now we only have one H right here, right? It will remove one of the protons and take it as itself. So here we go, bases add hydroxides, right? And they accept protons because ammonium here only had 3 protons and now it has 4, right? So interestingly enough, you don't have to have hydroxide, but it's for right now it's like the most common base, but there are other bases too. Like this one's that one's ammonia is a base too. But the most common bases are going to be, for at least for now, is going to be hydroxide. So just remember, hydroxide is your base that you're using now. But when you get to organic chemistry, there'll definitely be more. There'll be different bases that you can talk about. So, what are strong or weak acids or bases? Remember that strong means it completely dissociates in water, and then weak means it just partially dissociates in water. And so, excuse me, this is a list of strong acids right here. We already talked about hydrochloric acid in your stomach, hydrobromic acid, hydroiodic acid. All those are strong acids. Chloric acids, chloric acid, right? Both of those are strong. Nitric acid, we use nitric acid to like clean up chemical spills. So they're pretty strong. Sulfuric acid's very strong as well. And so there's also strong bases too. So any base that has a lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, or cesium hydroxide, those are very strong bases. And then also, calcium hydroxide, strontium hydroxide, and barium hydroxide. Those are also very strong bases. So notice that these are all hydroxides right here. They all have this OH right here. So again, like in the previous slide, you can have weaker bases, but the strongest ones are going to be hydroxides, at least in your case right now. You'll learn more about more bases later on in your chemistry careers. So strong or weak electrolyte means the same thing basically as strong or weak acid. A strong acid will also be a strong electrolyte, which means that it dissolves readily in solution and breaks up and dissociates completely, right? And so generally ionic compounds are strong electrolytes. Remember, like for example, salt. NaCl is a strong electrolyte because you put that stuff into water, and it will dissolve immediately. And then not only that, if you run electricity through it, it will make a very good conductor of electricity. Whereas if you put sugar into water, it will dissolve, but it will not conduct electricity as well, and the light bulb will not be as bright, right? So the question you can ask here is it ionic or molecular, right? If it's ionic, it's most likely going to be a strong electrolyte, and if it's molecular, it's going to be a weak electrolyte, right? So example here will be NaCl, right, or salt. That's the example there for an ionic compound, and then molecular would be sugar, right? And so if it's a strong electrolyte, that's like salt, it's going to be a strong electrolyte, right? So you can apply this to with bases, acids, and bases as well. If the base is an ionic looking kind of base, then it's going to be a strong electrolyte. If it's molecular looking, then it's going to be weak. So we have an example here, right? If the H, if it starts with an H or ends in an H, it's an acid. We already knew that, right? For example, HCl, right? Definitely an acid, right? Let me write that again. I don't know why it's so fat. HCl, that begins with an H, so that's an acid, right? Or the example here, this is actually a carboxylic acid. Sorry, I keep on mispronouncing that. It has an H at the end, right? And so that's going to be an acid as well, right? And then so if it's not on the list of strong acids, then it's going to be a weak acid because there's less weak acids than there are strong acids. Or did I say that right? What else? There are more weak acids than there are strong acids. So there's a list of strong acids, and so if they're not a part of that list, they're going to be weak acids. And so, and I already told you before, the most common one is acetic acid. This guy right here, he's a very, very weak acid, and you know him already because he's a vinegar, right? People put vinegar in their food and it's fine, but you wouldn't want to put hydrochloric acid in your food and drink it, right, or eat it. So again, strong acids are strong electrolytes, and weak acids are weak electrolytes, right? And then the same can be applied to bases, and so this here is ammonia. We saw ammonia a second ago right here, acting like a base, but again, ammonia is a weak base. It's a very weak base, because it doesn't have hydroxides in them, right? Because the OH, remember I told you that our strongest bases have hydroxides. So again, the same thing goes if it's not on the list of strong bases, it's probably going to be a weak base. And you see ammonia, it's not on that list, so it's a weak base. So here's your next question on active. Just go ahead and answer that question, and we'll keep going. So I was saying a second ago that whenever you have a plus, right, and you have an OH, right, whenever you have a proton and you have hydroxide, this negative is very attracted to that positive, and so you end up getting a water out of it. So generally what happens then is that whenever you add a base and an acid together, you get what we call a neutralization reaction, right? And the reason why is because neutralization reactions always result in water, which is this water that I'm talking about right here, and a salt. And it's the salt of whatever the acid came from, right? So here's the example, the most quintessential example, and you'll be doing I think you'll be doing a titration with this in lab. Not sure though. Or maybe you're doing it with acetic acid. I don't remember, but you're doing some kind of titration with some acids. But notice we have our strong acid right here, which is hydrochloric acid, and then we have strong base right there. We combine them together, right? We get water and we get a salt, right? And here is the common salt of sodium chloride. Of course, it doesn't have to be hydrochloric acid. It could have just been, maybe it was hydrobromic acid or something like that. Do the same thing again. All this stays the same. So instead of having sodium chloride, you'll have sodium bromide instead, right? So again, every time, just know that when you add an acid and a base together, you always get as a product water and salt. And so that's the neutralization reaction, right? You can always predict a neutralization reaction because you always end up with water and salt. So neutralization reactions are actually part of or a kind of metathesis reaction or double replacement reaction, because essentially what's happening here is the hydrogen is switching partners to get the oxygen, right? In the oxygen and the hydroxide there, and then the sodium is switching partners and getting the bromide. So it's basically a double excuse me, a double replacement reaction. And so here's the complete ion equation. Again, we very rarely ever make you write out a complete ion equation, but sometimes we might make you do the net ionic equation. And again, the only thing that changes here is we get a proton coming together with hydroxide to make liquid water, right? And so since liquid water is like the only thing that's not in aqueous, that's the only thing we show. Just like we would do in the previous lecture with the metathesis reactions or the double replacements, solids became the only thing that, like things that contributed to making a solid would be the precipitate, and that would be what shows at the end of a net ionic equation. Here, the only thing that becomes, that's not a solid is, not aqueous, right, is the water. So that's going to be what's going to be in this net ionic equation. So I just said this a second ago, but I'll just say it one more time, right? So the neutralization reactions are just like metathesis reactions, where there's like a double replacement. But sometimes you can have a double replacement that has three products. So here we have calcium carbonate with a solid. It's mixing with hydrochloric acid, but then it comes up with three products: calcium chloride, carbon dioxide, and water. So in this case, whenever you have a solid carbonate, right, or a bicarbonate, right? So when some people call this a hydrogen carbonate right here, but it's a bicarbonate. So whenever you have a bicarbonate or a carbonate, so bicarbonate is this one right here, where it has an H, so that's why we call it bicarbonate, right? Whereas this is just a carbonate, regular old carbonate. And you mix it with acid, what you'll get is always going to be a salt, right? Water, and then the one extra product is a carbon dioxide gas. So those are always fun reactions to do, because when you mix them together, they make a lot of bubbles, right? They'll do I can't remember the word now. Effervescence. That's it. Effervescence. They're very effervescent, right? And so here's another one here where we have sodium. This is sodium sulfide, right? And it will mix with sulfuric acid, and it will make sodium sulfate in the metathesis reaction, right? Because it's a double replacement. So sodium here is giving up its sulfur to get the sulfate, right? To get the sulfate ion. That's how you get sodium sulfate, which is soluble in water, right? But then, interestingly enough, the product is hydrogen sulfide gas, right? And so instead of having water be this product, you actually get hydrogen sulfide gas, and that actually like escapes and from the reaction as a gas. And funny thing too is hydrogen sulfide can also be it can also be an acid as well. And so if you've ever smelled, like, I think I told you this before, but if you ever feel like there's like a gas leak in your house or something like, because you have gas stoves or something, that gas actually smells that way because the gas company puts in hydrogen sulfide gas into the gas line so that if there's a gas leak, you can smell it and you can get at it before the thing explodes. Because methane gas or any of those liquid petroleums that you use for gas stoves, they don't smell like anything. They don't have, they're what we call odorless. So the smell of and it's the smell of rotten eggs basically, and it's a pretty strong smell. Humans are, for some reason, I don't know why, but humans are we're super sensitive to sulfur smells. Humans are. And so there's a compound that we use in my lab a lot called beta-mercaptoethanol. It's the sulfur compound, and holy mother, it smells like burnt butthole. It's so like every time someone opens the bottle, we know that someone's out there working it because it smells so bad. And there's also the smell of like demons too, I hear. So some these are some applications. These are some applications of neutralization reactions. Alka-Seltzer that helps with like acid reflux, right? So you have if you have like a really acidic meal or something like that, they recommend some kind of weak base to help you kind of calm down the acid reflux. So Alka-Seltzer is very common, but there's some other ones too. I've never heard of Amphogel, but that's aluminum hydroxide. Notice that's a hydroxide right there. D-gel, I've never heard of that one either. Magnesium hydroxide, calcium carbonate. I've heard of milk of magnesia. See another hydroxide there to help you neutralize the acidity in your stomach. It happens a lot after like pasta meals, like with with tomato sauce, things that are very, like I said, acidic. Maalox, definitely heard of Maalox. Mylanta, definitely heard of that. Definitely heard of Rolaids, Antoms. All those act the same way. They just kind of help you neutralize the extra acidity in your stomach. And so the last type of reaction, I think is the last one that we're going to talk about, is called the oxidation reduction reaction, where the species will either gain or lose electrons, right? So, and we've talked about this before, just not in this way, but if a species loses an electron, we call that an oxidation. But if a species gains electrons, we call that reduction. So the acronym we always use to remember it, right, is, my pen stopped working, there we go, is called OILRIG. What the heck? Let me write that again. OILRIG. There we go, right? So that is oxidation is loss, and then reduction is gain, right? Gain of electrons. And so OILRIG is, I don't know why I wrote another G there, but I meant for that to be an arrow. But that means that whenever, like I said, a species loses an electrons, it's called oxidation. Whenever a species gains electrons, it's called reduction, right? And so we call these redox reactions. And then in lab, I'm pretty sure you're going to do another titration that's called a redox titration. I don't know if you've done it yet or you will do it soon, but it's going to happen, right? And so here's a good example of a redox reaction. If we have solid calcium sulfate, solid calcium. I don't know if you remember this, but we can like add that to it's pretty it's very calcium is very reactive with the air, right? So it will react with oxygen, okay, to make a calcium oxide solid, right? And so what's happening here is that the solid calcium, which is what you see right here, it actually interacts with oxygen molecules, right? And when it interacts with the oxygen molecules, it just takes electrons from the from the oxygen molecules. And when it takes electrons from the oxygen molecules, um, so I'm sorry, not it doesn't take electrons. The oxygen molecules take electrons from it, rather, right? And when the oxygen molecules take electrons from it combines with it and it becomes calcium oxide, right? But if we look at a very close level, we can see that calcium, since it's losing electrons to the oxygen, is getting oxidized, and since oxygen is gaining the electrons, it's oxygen is getting reduced, right? So here, calcium is getting oxidized because it's losing electrons, and the oxygen is getting reduced because it's gaining electrons, right? It's gaining electrons. Notice we have also a balanced chemical equation, right? Two carbons, right? Two calciums right there, two oxygens right there, and then we have a big 2 right in front there to make 2 calciums, 2 oxygens. So that's a balanced chemical equation, right? So just remember, right? Calcium here is getting oxidized, and then oxygen is getting reduced, right? And so you can actually, it's a very easy thing to know how to do because we already talked about it in the periodic table. Because remember that calcium is in group 2, right? And so it's got a +2 charge. Why does it have a +2 charge? Because it loses 2 electrons, right? So it lost electrons, and what happens? It becomes oxidized, right? So anything that's in group 2 will get oxidized and lose 2 electrons, and that's why it has a charge of +2 to begin with. Because remember in the last section, we talked about how the group number tells you what the electrons, what the charge is, right? Same thing with group 1. If it's group 1, it will lose an electron, right? There are other metals that are in the transition elements that will lose, they have an option of losing more than one, but we'll talk about that in a second. But for group 1 and group 2, they're always going to be oxidized to be cations, right? Either with a +1 charge for the group 1 ones and then +2 charge for the group 2 ones. And then on the other side of the periodic table, right, remember that oxygen is in group 6, and so 6 minus 8 is -2, and that's why oxygen always is a -2 charge because it gets reduced, right? So anions are always going to be formed with nonmetals. Nonmetals always nonmetals always gain electrons, right? So they always get reduced to become anions. But on the test or something, or on a quiz or something like that, there will be questions I ask you that will ask you, did this thing get reduced or did this thing get oxidized? So you need to be sure you know how to do that. So this is number 7 right here. Go ahead and scan it, and we'll move on. All right, so how do we determine oxidation numbers? I already told you the easiest way to determine oxidation number is the group 1 thing and group 2 thing, right? Remember the periodic table. I'm going to try to draw one out here. This is going to look terrible. I could have just put a periodic table here, right? And then we have this over here, transition metals, right? We'll talk about the transition metals later. And then here's this, and here's this, and here's this, and here's this, my periodic table, right? So that's group 1 right there, group 2, right? And then 3, 4, 5, 6, and then 7, and then group 8. All right. So again, oxidation numbers are essentially the charge, right, of the species after it's lost or gained its electrons, right? So from here we have the metals, right? And if it's in group 1, it's always going to have an oxidation number of +1. And then if it's in group 2, it's always going to have an oxidation number of +2, right? +2. On the other hand, though, here we have our nonmetals, and don't forget that there's that little stair-step thing down here, right? So anything that's above the stair-step thing, right, we'll have our nonmetals, and so group 3 things will always have a -3 charge, right? Not -3, I'm so sorry. That should also be +3, right? And then after that is carbon is the only one. The next one is in group 4 is carbon. So carbon can either be plus or minus, right? I won't ask you about carbon much, but it will always be plus or minus. It can be plus or minus 4, right? Because it's kind of right in the middle. It's kind of right in the middle of everything, right? So, but then the easy stuff happens, right? The oxidation numbers will come from the subtraction of 5 of the group number from 8, right? So in group 5, then 8 minus group 5 is 8 minus group 5. Sorry, 5 minus 8 is minus 3, right? And then 6 minus 8 is minus 2, and then 7 minus 8 is minus 1, right? So you don't even have to worry about these guys so much here, right? These guys here, you don't have to worry about that much, right? Because we might ask you something about the plus 3 charge, like boron, and carbon, it can form 4 bonds, as you know already, too, like methane. I draw that for you all the time, right? That's methane right there. It can form 4 bonds. So, but really the thing you should memorize is these right here, right? So group 5 is minus 3, group 6 is minus 2, and then group 1 is minus 1. So of course, and then of course over here group 1 is plus 1, and then group 2 is plus 2, right? And of course, if you're a noble gas, you're at 0 because you don't want to give up anything anyway. Sometimes you can get noble gases to do things, but you don't have to worry about this. Worry about that in this class. Okay, so, and then we have our transition metals right here. They can lose anywhere from 1 to 3 electrons each. So that's why you get things like copper 1 or copper 2 or copper 3 or whatever, right? So these guys will always either have a charge of either plus 1 through plus 3. It just depends on the iron. The iron it depends on the atom. Okay, it depends on the atom. And normally the way you tell is by using the formula. The formula will tell you what the charge is, or what the oxidation number is, right? So these are just some like written out instructions for how to determine what the oxidation number is. Atoms in their elemental form always have an oxidation number of 0, right? Funny thing though, they still want to be close. They want to be like 8, so they'll lose or gain electrons to become 8, to have 8 electrons in our shell, valence shell, right? So, and then number 2, the oxidation number of a monatomic ion is the same as its charge, right? So this statement right here, right? That statement right there, that's this right here, right? The charge of group 1 is plus 1, which means that's oxidation number is 1. Charge of group 2 is plus 2, so the oxidation number is 2. And then over here, group 5 charge is minus 3, so oxidation number is minus 3. And then minus 2 and minus 1 and so on, right? So those are what those two statements say. And then we can go through some steps here. Nonmetals usually have a negative oxidation number, like I said before already, although sometimes they can be positive. So for example, oxygen is usually a negative 2. Why is it negative 2? Because it's in what? It's in group, oops, spelled it wrong, group 6, right? And so group 6 means that minus 8 makes it minus 2. So it always wants to gain 2 electrons, right? The only time that it's not a negative 2 charge is when it's in a peroxide ion, right? So that just means something like this, OOH, right? And so the interesting thing with that is that you can use this charge thing as and I said that a second ago, but you can use this charge as the oxidation number unless it's a part of a polyatomic ion. Polyatomic ions will have a different oxidation number for most of the atoms in the uh, um, in the polyatomic ion, right? So this peroxide that we have not talked about yet, we did a little bit because we talked about H2O2, which you shouldn't drink that, right? Because it's bad for you, it'll kill you, right? Which is the same. It's part of what this guy is right here, the peroxide ion. But that being said, though, that's still a polyatomic ion, and so its oxidation number will be different from what its charge is from the periodic table. And so just remember, though, it's the easiest thing to remember is, though, the charge is usually the oxidation number. So hydrogen, of course, usually always a +1, right? Always a +1. And so, but sometimes, when it's bonded to a not bonded to a metal, it could be a -1, and that's because, remember, hydrogen's on both sides. I told you hydrogen before. It's on, it could be on either side of the periodic table. Again, this is my periodic table, right here, right, and then hydrogen's over here, right? But hydrogen can also be over here too. That's why hydrogen's it's the only one that doesn't act like a metal. It can act like both. Fluorine, of course, group 7 means -1 charge, which means the oxidation number is a -1. But again, if it's in a polyatomic, like an oxyanion or something like that, it will have a positive charge instead. So some of those things you can just memorize too, or you can calculate them out. So then you can sum up the oxidation number in a neutral compound, and it should be 0, right? Because again, they all want to eventually come out as 0, right? In the end, they're going to have 8 electrons in their outer shell, but they also want to be 0 charge, right? And then so the sum of the oxidation numbers in a polyatomic ion is the charge of the ion, right? So for example, if you remember the nitrate ion, which is NO3, its charge is -1. So we use, if you get the oxidation number of nitrogen and an oxidation number of three oxygens, they will sum up, and when they sum up, they'll be -1, right? Or another good example is phosphate. It's -3 charge, right? And so oxidation number of phosphorus and oxygen number of 4 oxygens added together will make, or combined with each other will make -3, right? And so remember to count every atom, right? Especially in the polyatomic, no matter how large the subscript, when assigning oxidation numbers, okay? The other way to do it too is just to, like I said, if you have the formula, you can also figure out what the oxidation number is. Or you can also, just one more time, each individual oxidation number, you know what it should be from the product table because it's the same as its charge. And then when you combine them together, that's how you get, the overall charge of the polyatomic ion, and that's also going to be the charge of the polyatomic ion. So there's also these things called displacement reactions. These displacement reactions remind me of being in a relationship and then breaking up, and then your partner getting a rebound, right? A rebound. And so a lot of these these redox reactions that we talk about, they're see, it's hurting my heart. No, just kidding. They're displacement reactions, right? So here we have an example. We have hydrochloric acid, and we have magnesium. And so hydrochloric acid is done playing with, being itself, right? Oh, I should not do that because I want you to see the oxidation numbers. Let me erase that real quick. There we go. So hydrochloric acid right here, right? Hydrogen and chlorine are done. They're completely done in this relationship. They don't want to be together anymore. And the reason why is because chlorine, right, which is right here, chlorine found magnesium, right? And it's like, dang, I want to be with magnesium. The heck with this. I'm breaking up with hydrogen, right? And so when hydrogen, when magnesium breaks up, when chlorine or chloride breaks up with hydrogen, it gets together with magnesium, making magnesium chloride, and now hydrogen's just a gas and has to go away. It's very sad, right? It's like, it's almost like, no, it's not almost, it is. Hydrogen just got dumped by chlorine, dumped, and ghosted. And is that what you kids say these days, ghosted? And magnesium and chloride are now a happy couple, right? And so in this particular what happened here, right? We start out with uh, hydrogen and chlorine having plus and -1 charges respectively. So, magnesium, since it's just the solid magnesium, the remember just the atom on its own is always going to have a zero charge, or a zero charge, and also a zero oxidation number. And then when hydrogen and chlorine broke up, uh, uh, chloride broke up. Right now, hydrogen comes back down to zero. Because now it's just the regular old gas by itself, and so now magnesium has lost its 2 electrons to chlorine, to 2 chlorines, right? Which is sad for it, but maybe they're happier together this way. I don't know, right? So we want to talk about that I'm sorry, I said to chlorine, to hydrogen. Sorry. So in the breakup, right? In the breakup, uh, hydrogen ends up taking two hydrogens. Sorry, in the breakup, hydrogen ends up taking 2 electrons from magnesium, right? But magnesium doesn't care. Magnesium just wants to be with chlorine, so with chloride. So, um, uh, sorry, I'm getting text messages. And so what that means then is that hydrogen will oxidize magnesium, right? And you can see that in a little picture right here, right? There's the electrons right there. They're going towards hydrogen, right? And so that makes hydrogen gas. And hydrogen's like, man, if you're gonna break up with me, chloride, if you're gonna break up with me, I'm gonna take something and steal something from magnesium first, And so it's like that song where that girl and like hits breaks the headlight of that guy's car or whatever before they break up. Anyway, so chemically, hydrogen oxidizes magnesium, takes its electron, and it does that so that it becomes hydrogen gas on its own, floats away, and then that means it's been displaced, right? And so now magnesium replaces hydrogen in the reaction, and now chlorine. Um, Chlorine actually gets to be with hydrogen now, right? So, I mean, sorry, with magnesium now, so it's magnesium chloride. So, just to be clear, magnesium got oxidized and hydrogen got reduced, right? So when it says hydrogen or protons or whatever, H plus oxidizes the magnesium, that means that hydrogen, right, got reduced, and then magnesium got oxidized because it lost electrons. I don't even know how to draw. I can't even spell oxidized. Whatever. You know what I'm saying, right? So again, you just got to make sure that you don't get confused here, because if you notice here, chlorine has a -1 charge on the left hand side when it was with hydrogen, and then chloride had also still a -1 charge when it's over here as a product of magnesium. So nothing happened with chloride in this reaction. Chloride just broke up with hydrogen. Hydrogen was the one that went and took an electron from magnesium. That's why magnesium now lost 2 electrons. Both of them went to hydrogen, and that's why hydrogen now is a zero charge. So when you look at these reactions and I ask you what got oxidized and what got reduced, make sure you're paying attention to the oxidation numbers, because some people might just say that chlorine did it, was a part of the redox reaction, but no, it was hydrogen and magnesium that was a part of the redox reaction, right? And so this is the activity series. We won't do much about this, but just know that the ease of the oxidation increases as you go up this list, right? So things like lithium, very easily oxidized; potassium, sodium, very easily oxidized; but things like gold, platinum, mercury, very not easily oxidized. And so that's why I always tell you guys about the reaction when you when you throw sodium into water. So easily oxidized because sodium really wants to get rid of that electron, so it's easily oxidized, and it will react with water and then go explodey, and it's a really fun reaction to do. And then we have metal acid displacement reactions, right? This is again kind of it's kind of like a display. It's a type of displacement reaction. Here we have what is that? Silver nitrate with copper. And then, so what's happening here now is that nitrate is, ghosting or dumping silver, and then nitrate now becomes becomes a copper nitrate, and now silver is off on its own. And honestly, silver is better off on its own because it's more valuable that way. And so, and so again, this is kind of one of those reactions where you think that nitrate had something to do with the reaction, the redox reaction, but it doesn't. And so here we notice that once we have copper in the mix, right, it's going to lose some electrons right here to silver, right? And so it's just like the last one, where silver, after right before they break up, it's going to take some freaking electrons, take its due before it skedaddles, so that copper and nitrate can be together. And so in this case, again, copper is the one getting oxidized, and then silver is the one that's getting reduced, right? So remember, just try to make sure that you're not picking the wrong ions here to be a part of this reaction. And then so that's our next question. Go ahead and finish that one. Okay, so now let's talk about stoichiometric calculations. And really, this is going to be an extension of what we talked about in the last chapter, with talking about the mole ratio and balanced chemical equations with the coefficients, right? Where we convert grams to moles back to, or go from moles to grams. And what we're doing here now is we're going to try to figure out different amounts or quantities of reactants and products. And we can predict how much we're going to get using the mole ratio, right? And we talked about the mole ratio before. So it should look very familiar for you as we go through it all, okay? So let's start with this one right here as an example, okay? The question says, how many glucose molecules, how many grams of water can be produced from 1 gram of glucose, okay? So the first thing we have to do here, is we have moles of glucose, right? And we can convert that using the molar mass of glucose, right? And so we have a starting material here, which is 1 gram of glucose, right? And so for us to be able to get to what the number of grams of water is, we have to go through the molar calculation, or the stoichiometric calculation, of going through grams of glucose, using grams of glucose to get to moles of glucose, and then go from moles of glucose to moles of water, right? And then from that, moles of water to moles of grams of water, right? To grams of water. And so there we're doing, again, that's the molar ratio, right? When we talk about the moles of glucose to the moles of water, that's the molar ratio, okay? So what do I always say before you start one of these things? You always have to get the balanced chemical equation. This one's a little harder because there's glucose there, right? And so you have to figure out the balanced chemical equation. It requires 6 oxygens, right, to get the correct balanced chemical equation here. I won't ever make anything that difficult for you when you're doing these, but just remember that the first thing you have to do is always write out the balanced chemical equation, because the molar ratio you're looking for here is the 1 mole of glucose to the 6 moles of water, right? So you'll have to write it, you'll have to write it as the molar ratio, either as for every 1 mole of glucose over 6 moles of H2O, or you're writing it as 6 moles of H2O over 1 mole of glucose. And so just remember, though, this is what I'm talking about when I say molar ratio. Right? And you won't know this molar ratio unless you have a balanced chemical equation, right? I got the 1 mole of glucose, right? and the 6 moles of water from the balanced chemical equation. So that's very important, right? So let's go through and work this thing out, okay? So starting with 1 gram, and I really don't like that they did this, but this way, but so just don't worry about that right now. This should be dimensional analysis, right? Like this. And so here's your fence post, just like that, right? And so here we started with 1 gram of glucose, right? And so we want to cancel out grams of glucose, so that's why we use the molar mass of glucose right there, right, to cancel it out, okay? And so for every 1 mole of glucose, we have 180 grams of glucose. And now we have moles of glucose. But now we want to cancel out moles of glucose, right? Because we want to go from moles of glucose to moles of water. So here's your molar ratio right here. For every 6 moles of water, there is 1 mole of glucose. So this is the molar ratio. This is the important part. You won't be able to work this without this right here. So this is the molar ratio. So again, if you don't know what the molar ratio is, where did you get that from? We get it from the balanced chemical equation. There's no way to do it otherwise, you know. And so the one we used, the one that we used to do this one, right, is the one with 6 moles of water, right, over 1 mole of glucose that we got from the balanced chemical equation, because moles of glucose was at the top, right? So, no, I didn't mean to cross out the one. The one should stay there. Let me just undo that. Can I undo that? I just erase. There we go. Anyway, back to green, right? And so all that gets canceled out, and we're left now with moles of glucose are canceled out. So now we're left with our numbers with 6 moles of water, right? And so we want to figure out, I think the question asks how many grams of water, right? And so how do we figure out how many grams of water we have? Well, now we use the molar mass of water to figure out how many grams of water we have from the number of 6 moles of water, right? So continuing on, right? So we've already done all this stuff already from the previous slide. Don't write it that way. I don't like that. Don't do that. Just write it out as dimensional analysis like you're supposed to. Right. Whew. Okay, and so I think that's actually a typo there. It shouldn't be 180. Shouldn't it be just 18? So moles of water get canceled out with moles of water here, right? And so for every 1 mole of water, it should be not 180. That's a typo. That should be 18 grams of water, right? I'm pretty sure, right? Because oxygen is 16. So yeah, that's a typo, but that's okay. And then all you have to do is go through the math, right? Like we always do. Multiply all the things on top. So 1 times 1 times 6 times 18. And then multiply 180 at the bottom times 1 times 1. And then divide the 2 out. And then you should get 0.6 grams of water. I'm pretty sure that's right. Do the calculation yourself just to make sure. I don't have a calculator here with me in my hotel room. But I did notice, though, that is a typo. That should not be 180. That should be 18. So do the calculation. Make sure it's 0.6. If it's not 0.6, then correct me later, right? But yeah, that's how you do it. It's the same way that we did molar calculations before. And you'll be doing a lot of these. So here's your number, here's your ninth one. So in your ninth one, go ahead and answer that question, and then we'll keep on moving because we're almost done with this lecture. So what is a limiting reagent, right? Some people say limiting reactant. Some people also call it limiting reagent. And so the limiting reagent is the reagent that is, or the reactant, right, that is present, right, but it's in smaller amounts. And so if you don't have enough of it, it will run out of that first, right, in limiting reagents, right? And so it will run out first. And so the one that is present in the least or the smallest stoichiometric amount will be usually the one that's the limiting reagent here, right? So in this reaction, we have 10 moles of water and 7 moles of oxygen, right? And at the end of this reaction here, we have 10 moles of water, and then we still have 2 moles of oxygen left. and no moles of hydrogen. So what that means then is that we were still able to make these 10 moles of water. These two oxygen from the 7 here didn't even react because we ran out of hydrogen to use, right? And since we ran out of hydrogen to use, the hydrogen molecules are the limiting reagent. Some people call it the LR for limiting reagent, right? So using that, you can actually predict what your quantities are, right, for your products, using these stoichiometric calculations, right? Oh, and just if you didn't already know, if hydrogen is the limiting reagent, that means the oxygen, the stuff that's left over because there was not enough hydrogen, is the excess reagent. Because we still have extra of that left over, right? And I just said this a second ago, you can use stoichiometry to determine the stoichiometric calculations that determine or predict what you're supposed to be getting in yields, right, from your products, like actually in grams, okay? Okay, so we will use our reaction between hydrogen and oxygen from our previous slide as our example for this problem, right? Where it's asking us it's asking us if we had 150 grams of hydrogen gas and 1,500 grams of oxygen gas, right? How many grams of water can form, right? So this is actually a very practical limiting reagent kind of question because hydrogen gas and oxygen gas combine together to make water in a hydrogen fuel cell, right? So it's a very practical application. So for this particular question, it looks like I'm asking you limiting reagent, but like, dang, there's only 150 grams of hydrogen. And there's 1,500 grams of oxygen. Obviously, the limiting reagent is going to be the hydrogen, right? Well, it's not always that obvious, and so you actually have to go through and do your stoichiometric calculation with both of the reactants and figure out which one is the limiting reagent by the one that creates the least amount of product, right? So we'll go ahead and do that now. And this is how you do all limiting reagent problems, okay? So we'll start out by saying, we'll start with hydrogen because it's first in the reaction right there, right? So I have 150 grams of hydrogen gas, right? Because it says right there 150 grams of hydrogen gas, okay? I got to convert that to moles, so I know that there are 2 grams of hydrogen gas, right, for every 1 mole of hydrogen gas, right? Because hydrogen is 1, right, and times 2, because there's 2 of them there, is 2. And again, I always forget to do my states, so don't forget to put your states in there too. It just kind of helps you remember things. So now that I've converted the hydrogen gas from grams to moles, I need to use the molar ratio. And this is why the balanced chemical reaction is so important. For every 2 hydrogens, I have 2 waters. So for every 2 moles of hydrogen gas, that looks really messy. I'm going to fix that. I'm also going to fix this too because it looks messy. It bothers me. I'm OCD that way. H2 gas, there we go. H2 gas. We have 2 moles of water, which is a liquid. So, yep, don't forget, this is the molar ratio. And you can only get that from getting the balanced chemical equation, and it's super important. It will all be wrong if you don't do that. So now that I have moles of water, I've got to convert that to grams of water. So I know that 18 grams of water is equal to 1 mole of water. That's because oxygen is 16, and the 2 hydrogens added together makes 18. Liquids, both of them. And now I just go through and do the math here. Multiply 150 times 2 times 18, and then divide it all by 4 because 2 times 2 is 4. And so the number I get here is 1,350. It even gave, so this is nice, right? They gave you here 2 significant figures, so you need to do it in 2 significant figures. I have 3 there, so I'll just round this up to 1,400 grams of H2O liquid. Okay. So we did that with hydrogen. Let's do it with oxygen now. 1,500 grams of O2 gas now. Set up my fence post. And then so for every 32 grams, I think, of oxygen gas, 32 because oxygen is 16 and there's 2 of them, I get 1 mole of O2 gas, right? And now I've got to do the molar ratio. This is a different molar ratio now. 1 oxygen mole, 1 mole of oxygen for every 2 moles of water. So for every 1 mole of O2 gas, I get 2 moles of H2O liquid. And then now the same thing as before, I got to convert those moles of water to grams of water, and so that's 18 grams of H2O liquid. Wow, that's really messy. I'm going to fix that. There we go. 18 grams of H2O liquid, and that's 1 mole of H2O liquid. Not H2O2. That's bad. It's not H2O2. Not hydrogen peroxide, that would kill you. Don't drink that. Liquid. Okay? So when you do that math, you end up with 1687.0. 2 sig figs, I'll just round it up to 1700 grams of H2O liquid. So notice, right, the one with the least amount is definitely the water, right? But I think the thing that is surprising is that there's such a big difference between 150. Whoops, sorry. There's such a big difference between 150 grams and 1500 grams, and you think that would be like the same would happen over in its products over here, but I mean that's a pretty close number comparatively, right? So you definitely have to go through and do these reactions, these reactants individually to figure out which one is going to be the limiting reagent. So you would say now, the hydrogen gas, H2 gas, is the LR for short, limiting reagent for short, right? And that's how you answer that kind of question. All right, so there's this thing called theoretical yield, and that thing that's called theoretical yield is literally this right here. It's the amount of grams that you calculated stoichiometrically that you could make, right? And so that's called the theoretical yield. Like if you go through, if you have a number of grams of something, right, of a starting material, and you want to figure out what's the maximum possible you can make of that product using stoichiometric calculations like we just did right here, that's called the theoretical yield. And then we also have the actual yield, right? And this is the stuff after you do the reaction in the lab, right? You go weigh it out on a balance, and then you see what your yield is, and that's called your actual yield, right? And so if you take your actual yield and you divide it by your theoretical yield and multiply that by 100, you get the percent yield. And so you're shooting here for getting as close to 100% as possible, and that means that you did a good job on your reaction, right? So let's just do a really quick example here. So with actual and theoretical yield, I would not use the rounded form of the product grams in there. I would actually use the unrounded, right, first, and then you can round later. And so I'm just going to use 1687 for this one. And so all I have to do here is percent yield equals, and then so for the theoretical, I calculated earlier, like in the previous slide, was 1687 grams, right? Times 100, and then let's say my actual yield was terrible, and I got only 168.7 grams, right? So I do that math, and I get 10%. That's terrible yield, right? You're shooting for something a lot closer to 100. But anyway, that's how you do a calculation for theoretical yield. I mean, sorry, for percent yield, right? It's a pretty simple calculation. So here's your last active chemistry question. Feel free to do that, and then we're going to talk about our very last topic for this unit, which is titration. What is titration? Well, titration is a technique we use in analytical chemistry, where we have like an unknown concentration of acid in a flask, right? we'll add to it an indicator solution, usually phenolphthalein. It turns pink when things get basic. And so what we'll do is that we'll have a standard solution in this big long glass tube here called a burette, right? And the burette has graduations on it, so you can kind of keep track of how much you're putting into the flask. But you put the known solution or the standard into the burette, and you drop it into the unknown flask until the flask turns pink. Not this pink too, though. This pink is way too pink. We're talking about a very, very light pink color, okay? And so that light pink color, barely noticeable, right? But the light pink color is what you're shooting for. And so that is going to be the endpoint, right? The endpoint tells you that the reaction is basically finished. And then so, but the other term known is the term equivalence point, which is the point at which there's the same number of moles of acid molecules as there are base molecules. That's called the equivalence point, right? And so knowing that, we can use the equivalence point to figure out the concentration of the unknown acid from a known base or a standard solution of a known base, right? And so and then the way we figure it out is by using molarity calculations and stoichiometric calculations. So that's why titrations are so useful, and you have to do them, right? And I think you'll do plenty of these titrations in lab, mostly with phenolphthalein. You already did a titration before with the copper chloride, so it's the same thing, same kind of thing, right? But this time it's acid base, and and these are with acids and bases, right? And when they combine, they neutralize each other, right? And so that's why we get an equivalence point where there's an equal number of acid and base, and we can use that as for information for figuring out a unknown solution, unknown concentration or something. So generally, though, just so you know, there's always a known or a standard or known. Some people call it known concentration of something up here. Generally, it's a base. And then you drip that down into this down here, which is the unknown. Oh, sorry, I can't even read that. Can you read that? Yeah. Oh, I didn't mean to erase everything. Well, that's okay. But I'll just write that again here. So this is usually where the known, right, standard concentration is, and that's usually a base. And then down here is always like the unknown, and that's usually an acid. And I say usually, but sometimes it can be reversed. You can do it either way, right? But usually that's what happens. And again, you're going for this light pink color to get you to the endpoint, which is essentially the equivalence point. So, and I talked about this already, right? Standard solution, right, which is usually a base that's in the burette, and then the equivalence point is when you have the same number of, the reaction is complete and you have the same number of moles of acid and base, and then the end point is when you get the color change to the light pink. So I talked about that already. So let's just jump right into an example, right? So here it's a little bit backwards, so don't freak out. They're still calculated the same way. I have an unknown solution of sodium hydroxide this time instead of unknown solution of acid. But again, we'll go through the process and you'll see you can do it either way, right? And so always start with what you have. And so we have here 45.7 mils of a 0.5 molar solution of sulfuric acid, right? So what is always the first step? The first step is always to have a balanced chemical equation. So I'll write out the equation first. Sulfuric acid plus sodium hydroxide makes water plus sodium, and then if you remember, sulfate here actually has a -2 charge, so we need 2 sodiums for every sulfate, right? So that's the chemical equation, but it's not balanced yet, okay? So how do we balance it? Why do we need to balance it? Well, notice I have 1 sodium over here and I have 2 sodiums over here. That's the biggest difference, right? And so that violates the law of conservation of mass right there. How do I create a second sodium out of nothing? That kind of thing. But then the other thing too is that we have 3 hydrogens on the left side, and then we only have 2 hydrogens on the right side, right? So this actually is a very easy balance. If you just put a 2 there in front of the sodium hydroxide and a 2 in front of the hydrogen, for the water, then you get everything is balanced, right? So now there are 2 sodiums, right, and 2 sodiums, and then there are also 6 hydrogens, because 2 times the oxygen right there makes 6 hydrogens. 4 here, sorry, hydrogens, oxygens. 4 oxygens plus 2 oxygens from there is 6 oxygens, and then this 2 times that oxygen right there makes 2 oxygens, and 4 makes 6 oxygens, so that's 6 oxygens on both sides. And then hydrogens, right? We have 2 here, and then 2 here from the sodium hydroxide that has a 2 in front of it, and we have 2 times 2 here makes 4. So now we have a balanced chemical equation, and the balanced chemical equation is important, as I always say. All right, so this is before we do any stoichiometric calculation, we have to get the concentration to something that we can use with moles, right? And so you already know the equation: molarity equals number of moles divided by liters, right? And so look what you have here. You have a volume here, and you have a molarity there that you can use to figure out the number of moles. This is what you're solving for. Solve for this. So you can use stoichiometric calculations with the molar ratios, right? So that's easy. 0.500 molar of the sulfuric acid equals, I better put that down there so we don't get confused. Sulfuric acid, right? AQ. Oh, I always forget that. Don't forget the AQs. AQ. AQ. This is just water, which is a liquid. And then this is AQ. Don't forget your states, okay? And then we're solving for X number of moles, right? So this is what you're solving for right there. And then you have our volume, which is 45.7, which converts to 0.0457 liters, right? So just solve for X, right? And when you solve for X, what you're going to get is X equals 0.02285 moles of H2SO4, right? AQ. That's great, because now you have moles of H2SO4, okay? You can take that into a stoichiometric calculation to figure out the rest, okay? So we'll say 0.02285 moles of H2SO4 AQ in our fence post. And then this is where we need the molar ratio, which we have from the balanced chemical equation. For every 1 mole of sulfuric acid, we have 2 moles of sodium hydroxide, right? Because we're looking for the unknown sodium hydroxide solution, right? So for every 2 moles of H2SO4AQ, we have 1 mole. Oh, I messed up. It's actually for every 1 mole. I said it backwards. Sorry about that. There we go. So every 1 mole of H2SO4AQ, we get 2 moles of, why am I messing up this so much? Sodium hydroxide, AQ. Right? And when we solve that, because we're just looking for a number of moles of sodium hydroxide, right? When we solve for that, we get let's see here, 0.0457 moles of NaOH, AQ. That's great. Now we have a number of moles of sodium hydroxide, right? And remember, the neutralization point, or sorry, the equivalence point, is when there's the same number of moles of sodium hydroxide as there is of sulfuric acid, right? So all you have to do now is use this with a volume of sodium hydroxide and figure out what the concentration is, and that solves the problem. And you're told right here that you have 20 mils of sodium hydroxide, right? So molarity of NaOH, oopsies, molarity of NaOH equals the 0.0457 moles of NaOH, all divided by 20 mils, or 0.020 mils of NaOH. Right? So we solve for that, and we get now the molarity to be 2.285 molar NaOH AQ. Honestly, you don't have to put AQ there because molarity already means that it's dissolved in water anyway. So you can just put NaOH. It's perfectly fine to do that. And then, so I guess the one thing left to do now is significant figures. All these have 3 significant figures, so I'll just round this to 2.29 molar NaOH. Yeah, you don't need to put the AQ there for that because it's not an imbalanced chemical equation. It's just a thing, and molarity already indicates that it's in liquid anyway. So that's how you solve for that. It's pretty easy. So that ends the lecture for today. By this time now, you should know how to do the law. You should know what the law of conservation of matter and mass is and how it relates to stoichiometry. You should know how to read and balance chemical equations and then identify and describe those types of reactions that we went through. Also know how to perform stoichiometric calculations, and then also know how to calculate the limiting reagents and theoretical and percent yields. And now you should also know how to perform titrations. All right, so that's it for this particular chapter, and what's going to happen now is, so the next time I'll see you will be on Monday, but just keep on practicing those, the discussion question, the discussion homework worksheets I posted for you on Canvas. All right, and I'll see you on Monday. Thank you.